The Spanish Royal Society of Physics, and with the support of the Ramon Areces Foundation. First of all, I would like to once again extend my gratitude to both institutions, which are represented here by President of the Royal Society, Adolfo de Azcárraga, and from the Ramon Areces Foundation, Professor Manuel Aguilar Benítez. Today, we have the privilege of having with us Professor Anthony Leggett from the University of Illinois, and as you probably know, Nobel Prize in 2003 for his achievements in the theory of superconductivity and superfluidity. Don't know if all of you know that this is not the first time that Professor Leggett comes to our university, to our faculty. Fortunately for us, he maintains a long-standing collaboration with members of our staff, in particular with Professor Fernando Sols, who is also with us here, joining us at the table, and who will make in a minute a more detailed presentation of the speaker's bio. So I just want to say that among the many achievements and recognitions that Professor Leggett has, there's one which is especially important for us. He's honoris causa doctor by this university, by the University Complutense of Madrid. He was awarded this honorary degree in 2011. And precisely the person who made the so-called Laudatio presentation was Professor Sols here. So in this way, the link is once more very strong with us. I don't have much else to say, just to say thank you to Professor Leggett for being with us again. I hope you enjoy very much your visit, as much as we will enjoy your talk, I'm sure. And for all of you, thank you very much for coming. Thanks a lot. Okay, now I will pass the floor to Professor Manuel Aguilar Benítez from the Ramon Areces Foundation.
Good afternoon. I am afraid that I have to follow the instructions from the director of the Fundación Ramon Areces, and I have to say a few words, but preferentially in Spanish, so I will apologize for that. So what I will say is very briefly make an introduction of what is the role that the Fundación Ramon Areces, and I will do so in Spanish. La Fundación Areces tiene entre sus objetivos tratar de acercar la ciencia a la sociedad española, reconociendo que hasta cierto punto la sociedad civil española es, científicamente hablando, relativamente analfabeta. Y trata de corregir esto con un programa extenso de actividades y de ayudas a la investigación en forma de becas, de patrocinio y financiación de proyectos científicos y tecnológicos, y de multitud de actividades como puede ser la organización de conferencias, de simposios y de seminarios y conferencias. Y normalmente organiza estas actividades en colaboración con instituciones que tengan objetivos afines. En particular, con la Real Academia de Ciencias, con la Real Sociedad Española de Física y con múltiples universidades y otras instituciones, tanto en España como en el extranjero. Un ejemplo de este esfuerzo colaborativo es el acto de hoy, y que se organiza en colaboración con la Real Sociedad Española de Física. El presidente nos dirá unas palabras a continuación, y también con la Facultad de Ciencias Físicas de la Universidad Complutense de Madrid. Por lo tanto, quiero agradecer en nombre de la Fundación Areces, a cuyo Consejo Científico pertenezco, pues la ayuda, el apoyo y las iniciativas tanto de la Real Sociedad Española de Física como el trabajo que ha hecho el decano de la Facultad de Ciencias Físicas y su equipo para tener hoy la extraordinaria ocasión de escuchar a una figura tan relevante como es el profesor Sir Anthony Leggett. So this is basically what I want to say concerning the Fundación Areces Foundation. I think that for us it's a magnificent occasion to listen to a person who has devoted his life to one of these emerging phenomena which are called superconductivity and superfluidity. It's really a very fascinating subject, and I can tell that because I have been working in some of these things in the past, and I am sure that the conference of the Professor Leggett is going to be really absolutely extraordinary. So thank you to the people who have contributed to the organization of this conference, and thank you to Professor Leggett for being here with us, and I am sure that we are going to be delighted with the thing that he is going to tell us in a few minutes. So thank you, and enjoy the session.
Okay, thank you very much, Professor Azcárraga.
Well, I intend to be exceedingly brief because we are all wanting to hear Professor Leggett. I will just say that we are very happy having here our illustrious guest who has kindly accepted the invitation and to participate in one more of these series of conferences that we organize. The scientific introduction will be made now by Professor Fernando Sols, who you all know very well, because he has been an old collaborator of Professor Leggett. And having said that, I will pass the microphone to Professor Sols. Thank you.
Okay. Thank you very much, Professor Sols.
Okay. Very well. Okay, thank you very much. Well, I thank everybody that has been involved in the organization of this event, and also the audience that is coming here. And I will talk a little about the figure of Tony Leggett, which many of you already know. But okay, so Anthony Leggett studied first classical philology and philosophy in Oxford, and then when he was 21, he decided to move into physics. With an extremely limited scientific background, okay? And only 5 years after that, he finished his PhD in Oxford in theoretical condensed matter physics. Then he was a postdoc in Urbana, Illinois, and in Kyoto, in Japan. Then after that, he got a permanent position in Sussex, in the United Kingdom, where he was a lecturer. And then since 1983, he became a MacArthur professor at the University of Illinois in Urbana, so he went to the United States, and he has been there ever since. When he was in Sussex, he did his most important contributions to the theory of the superfluid 3, which much later, in 2003, earned him the Nobel Prize in Physics. Other important prizes that he has obtained are the London Prize in Low Temperature Physics, the Wolf Prize from the State of Israel, and he's a member of the he's a fellow of the Royal Society and a member of the National Academy of Sciences. Also, when he was in Sussex, he began to do major work on another topic together with Caldeira, which was about the theory of the dissipation in macroscopic quantum systems. Interestingly, his work on quantum dissipation has many more citations than his work on superfluidity, which earned him the Nobel Prize. So what I mean by that is it's a work that has also had a tremendous impact. In particular, he focused on the quantum mechanics of macroscopic variables such as the relative phase of a Josephson junction or the flux through a squid, which is a superconducting ring interrupted by a Josephson junction. Now, the quantum mechanics of squids, whose understanding he pioneered, is now a reality, and in fact squids are among the main candidates for the first realization of a quantum computer, and as far as I can tell they are winning the race, it appears, okay? And all that started with the work of Tony, which began to speculate with quantum mechanics of a macroscopic variable such as the flux through a squid. He has also made, of course, many of the important contributions. I can highlight here his work on the effect of cosmic rays in helium-3, that they can help to nucleate the various phases of helium-3. Also in high-TC superconductivity, he has done important contributions, in particular the famous experiment of Illinois, in which the symmetry of the order parameter was identified, was essentially proposed by him, and he's one of the co-authors, together with some experimental physicists of Illinois. It's also important to remark his interest in philosophy, which motivated from early, well, he began studying philosophy, and he went to physics partially motivated by philosophical questions, and in particular he was always willing to understand and to test quantum mechanics at the macroscopic level, and that's why he began to be interested in superfluidity and superconductivity. In particular with Garg, with Anup and Garg, he generalized Bell inequalities to macroscopic quantum systems, which is also an important development. Anyway, as the Dean has said, he also holds among his awards an honorary doctorate from the Universidad Complutense, so in a way he's part of the staff of the Complutense, so then it's fair to say welcome back home, and we give you the floor now. Thank you.
Alpha, beta, gamma, delta. Yes, the microphone works. Good. Well, thank you very much, Professor Souls. Kind remarks. It's a great pleasure to be back here, and I'm very grateful to the various people who've been involved in organising this event. So, my question is, what is superconductivity? And just pointer, right. And if I wanted to demonstrate the phenomenon of superconductivity in a high school or undergraduate laboratory, what would I do? Well, crudely speaking, I'd do the same experiment which was done by the Dutch physicist Kamerlingh Onnes more than 100 years ago. And it goes like this. Let's see. Get this to work. Yep. We have a circuit here which consists partly of an uninteresting metal, say copper, which is actually not going to be a superconductor. And then we have a piece of the circuit which is, say, aluminum. And what we're going to do is to drive a fixed current through the circuit and measure the voltage drop across the aluminum. Well, what do we find? Not surprisingly, generally speaking, we find that the voltage, if we do this experiment at room temperature, say, we find that the voltage across the aluminum is proportional to the current flowing through the circuit, and the ratio of these two quantities is what we normally define as the resistance. So that's nothing but good old Ohm's law. However, if we go down lower and lower in temperature, well, the resistance decreases gradually as a function of temperature. But then, at a particular point, this is actually a bit high for aluminum, it's more like Kamerlingh Onnes' sample, mercury, the resistance appears to drop discontinuously to zero. So the current is flowing through the aluminum without any voltage being developed across it, essentially zero resistance or infinite conductivity. Well, that's the simplest experiment, but actually it doesn't really express all the interesting features of superconductivity. We now know that superconductivity is not one phenomenon, but a complex of phenomena which, generally speaking, seem to go together. So this is just our original experiment, but in some sense we can analyze this in terms of two different phenomena. And it's easiest to think about these, it's easiest to think about a ring made of pure, let us say, aluminum here. We find that if we generate a current around this ring, for example, by applying a pulse of voltage, then that current is going to be astronomically stable. It'll flow for as long as the ring remains in the superconducting state below its so-called transition temperature, T sub C. And in some sense you could say that's the closest to the original experiment. However, there's a second phenomenon which is associated with superconductivity, which was really only discovered 22 years later. That is perfect diamagnetism. When a metal, like aluminum, goes superconducting, then it will completely expel an external magnetic field, and the result of that, as we'll see in a moment, is the phenomenon of superconducting levitation, among other things. Now, there's no a priori guarantee that these two phenomena always go together. The theory suggests that under most circumstances they should, and experimentally indeed, they do seem to go together under most circumstances. So let's just take a look at this second phenomenon. This is the result of the expulsion of the magnetic field. So I have first a still photograph here. This is, you see that this is actually a little magnet which is floating above a superconducting pellet. Now I'm going to show you a short video here, and I would ask you to look at this video rather carefully, and I think what you should see is that initially the magnet, this is a little magnet here, here's a superconducting pellet, and let me go ahead with this if I can. Let's see if that works. Does that work? Yes, here we go. Oh, yes, you see, nothing special. This is room temperature, nothing special about it. Now, the experimenter is going to put the magnet above the superconductor, and the glass plate basically is just to keep them separate. Now watch carefully, you should see that at some point there's a slight lift of this magnet here. I don't know if you saw it, but the magnet did actually lift off slightly, the glass plate, right? And I can assure you, I've done this experiment. I think we'll stop the video at this point, but I can, if I can do it, yes, yeah. So I can assure you, I have actually done this experiment many times in front of various school children groups, and indeed the magnet does lift off. That's very important. So that's not the same as infinite conductivity. It's a different effect, though it's strongly related. So we have these two phenomena then, persistent currents and the expulsion of a magnetic field which leads to this superconducting levitation. Okay, so now let me try to explain, at least crudely, how we can understand at least one of those two phenomena, namely the persistent currents. And this goes back to a very basic idea in the physics of elementary particles, like electrons, protons, neutrons, and so forth. In quantum mechanics, particles essentially behave under some circumstances like waves, and therefore it's impossible to put tags on them. So suppose we start off with two particles, let's say electrons, which we just call Bob and Fred here. We start them off at a particular position and we let them go. They basically propagate as waves. So when we look at them at the end of this process, if we ask which is Bob and which is Fred, there's really no way of telling, because they could have done this or they could have done this. And if we're talking about elementary particles, there's no way of telling which they are. So these these particles are completely indistinguishable. However, you notice that in order for that property to matter, the particles in question must be able to change places, and indeed they can, for the electrons in a metal. Now, it turns out, and this is not at all obvious, I have to tell you this, but it turns out that this property of indistinguishability has various very interesting consequences, and one of them is the so-called quantum statistics that's obeyed by elementary particles. Turns out that elementary particles actually come in two different kinds, and they're distinguished by whether the so-called spin, the intrinsic rotational motion of the particle, is integral or half integral in terms of a certain basic unit, which we needn't worry about for present purposes. One kind of particle has spin a half or three halves or whatever. These are called fermions, and fermions are very xenophobic. They will tolerate at most one particle per state. Therefore, at low temperatures, what tends to happen is that the particles occupy the lowest energy states up to a certain, approximately a certain energy, which we call the Fermi energy, and thereafter the distribution falls off to zero. So it's rather boring. And the electrons in a metal are fermions, and so in the normal state, so at room temperature, this is roughly what's happening. And it's sort of pretty boring from a, well, it's not totally boring, a lot of interesting things go on, but it's not spectacular. The second class of elementary particles have spin 0 or 1, whatever, and these are called bosons, and this kind of particle is extremely gregarious. So much so that you love to have lots and lots of particles in the same state. And so if I go to low enough temperatures with a dense enough system, then I find that there's a certain population of states with non-zero energy, but then you get a macroscopic number of particles, a finite fraction of all the particles condensed into a single state. And that's the phenomenon which we call Bose condensation or BoseEinstein condensation, after the people who first realized it. And the interesting thing about this state, here we are, yep, okay. This is a picture which appeared on the cover of Science magazine in, I think, December 1966, which was when a particularly important kind of Bose-Einstein condensate involving ultra-cold gases was discovered. And it shows the Bose condensate as a platoon of soldiers all marching exactly in lockstep. The crucial point, they're all doing exactly the same thing at the same time. And these guys out here, they're the atoms which were not Bose condensed, so they're all each doing their own thing. But the Bose condensate is such that each of all the atoms in it are doing exactly the same thing at the same time. Now, the electrons in metals actually have spin a half. And so they are fermions, and at first sight, you'd think, therefore, they must always behave in the rather boring way we saw earlier. And indeed that's true at room temperature, or thereabouts. However, it turns out that a compound object, which consists of an even number of fermions, has spin 0 or 1 or 2, and therefore constitutes a boson. And then an example of that, for example, is that the helium-4 atom, which we normally treat as a boson, is composed of 2 protons, 2 neutrons, and 2 electrons, so 6 fermions in all. But nevertheless, it behaves as a boson. And therefore, it can undergo Bose condensation. So what we think happens in a superconducting metal is roughly this. You might think at first sight that two electrons get together to form a tightly bound dielectronic molecule, like so. And these then might undergo Bose condensation. That might be true for some of the newer superconductors, but it's almost certainly not the case for old-fashioned superconductors like, say, aluminum or mercury. In those cases, what happens is that you do actually form a sort of dielectronic molecule, which is called a Cooper pair. But the electrons in the Cooper pair, which form the Cooper pair, are very far away from one another. And so in between them, there are lots and lots of other electrons, each forming their own Cooper pairs. So people sometimes compare this to a form of modern dance in which I might be here and my partner is way across the room over here, but nevertheless my motions are correlated completely with those of my partner, despite the fact that all these other couples forming their pairs in between. Well, it turns out very, not obvious, again I have to tell you this, it turns out that in the simplest theory, the so-called BCS theory, due to my former colleagues Bardeen, Cooper and Schrieffer at the University of Illinois, in that theory, once the Cooper pairs are formed, they must automatically undergo Bose condensation. And therefore they must all do exactly the same thing at the same time. And it doesn't matter whether you're talking here about an equilibrium situation or a non-equilibrium one. So all do the same thing at the same time. So how does that help to explain one of the phenomena of superconductivity? Let's think about the phenomenon of persistent currents. So we apply a transient voltage around this ring. We can do that, for example, by turning down the magnetic flux through the ring. That will generate a transient voltage around the ring. And if the ring is in the normal state, what's going to happen is that a current is excited, but it rapidly dies away. And the higher the resistivity, the faster the decay. Nevertheless, if we take the ring down in temperature into the superconducting state, then when after we generate the initial current, it will persist essentially forever. In other words, the resistivity will go to zero. So that's the phenomenon then of persistent currents. The question is why? Why does that happen? And here's a rather simple, but I think nevertheless in some ways accurate explanation of what's happening. Let's make an analogy. Let's imagine we have a forest, not a plantation, but a natural forest with the trees distributed at random. And imagine, first of all, that we take a group of school children and we tell them to run into the forest, but we give them no special instructions. What's going to happen? Well, the school children are going to start running into the forest, but sooner or later, one of them is going to run up against a tree. And so she'll swerve to avoid the tree, and since she has no special instructions, she'll go on running in the new direction. And therefore, after a fairly short time, you'll find that the children are all running around in random directions. That's truly speaking what happens in the normal metal. You start off the current, it's composed of normal electrons, and they run up against impurities, they get scattered, and they end up running around at random, no current anymore. Now let's consider a different situation. We now consider a platoon of soldiers running into the forest. And the platoon of soldiers has instructions that as far as possible they are to keep in step and all behave at the same way at the same time. Then, well, the first soldier runs up against a tree, and so he will swerve to avoid it. But he has instructions that he has to keep in step with his fellow soldiers, and so he gets back into line afterwards. And this process goes on, and so even after a long time, the soldiers are still marching in step in the same direction. And this is the analogy of what happens with the Cooper pairs in superconductors. As you remember, they have to keep in step, they have to all do the same thing at the same time, and therefore even if one of them is scattered, it doesn't matter, they'll drop back into line, and so forth. So as I say, that's a hand-waving explanation of the phenomenon of persistent currents, but I think it does in some sense embody the real physics. However, that's fine, but wait a moment. Persistent currents are not the only signature of superconductivity. What about the Meisner effect, so-called? That's the exclusion of magnetic flux. That's what leads to superconducting levitation. As I mentioned previously, this contrary to what you'll find in some not so good textbooks, the Meisner effect is not just a consequence of zero resistivity. In fact, it took 22 years after the discovery of zero resistivity to discover the Meisner effect. Well, it turns out, this is a little more difficult. It turns out that indeed the Meisner effect is a consequence of Bose condensation. However, I'm afraid the explanation is a little too complicated for me to give it in a 1-hour talk like this. And I'll have to just ask you to take it on trust that effectively it turns out the superconductor is behaving like a giant closed shell atom. And you might remember that closed shell atoms do tend to show diamagnetism. The superconductor is doing the same, but in a much more spectacular way. Okay, let's go on at this point and then ask, okay, very crudely, materials, including aluminum, are superconductors, that is, they have zero resistance. Now, imagination of superconductivity. Now let's go on and ask, what's it good for? Something like somewhere between 8 and 10% of the current electricity which is generated. There are some other advantages. The magnetic levitation phenomenon, which I showed you a video of, and just to illustrate the fact that you only saw a superconducting pellet, you might want to pass this around. So already, if you can get your superconductor to low enough temperatures, then you can even levitate a sumo wrestler. So that's not bad. If we could do this at room temperature, well, then we get into the science fiction regime of people floating around on superconducting chairs and so on and so forth, and it would be great fun. Alas, there's one slight problem. In most materials, drop to zero at Tc, but Tc is only about 1.3 degrees absolute. That's about 1/300th of room temperature. So you can get there, but it requires a lot of special apparatus and so forth. Not terribly good for practical applications. So why? Well, we do, I think, understand a little about why the transition temperature is so low, and the explanation is roughly like so. I'm just recapping now what I said earlier. According to the principles of quantum mechanics, particles can be classified into two types: fermions, which are very xenophobic, and bosons, which are very gregarious. Under appropriate conditions, bosons do display condensation directly. However, two fermions make one boson, so if we can get the electrons to form pairs, that is, dielectronic molecules, then the pairs can undergo Bose condensation. Now, to form molecules, dielectronic molecules, so initially you have a set of ions which are positively charged sitting around at these points here. Electron number one comes through. It's negatively directed towards the region through which the first electron passed. And so you get an effective interaction, an effective attraction between the two electrons themselves, and the second person then sort of tends to fall into it. So you get an effective attraction between the two sleepers, and basically that's roughly what's going on here. But conductivity was discovered, but for example, the application to large-scale power transmission or to reasonable, efficient magnetic levitation is explanation. Associated with the ionic lattice. As to the factor, well, within BCS, there are strong arguments that that factor can be degrees absolute. That's about 1/10 or 1/8 of room temperature. That actually we got quite a big surprise, very large special exception, and since you have many times you need in which the transition temperature is much higher. And in fact, it's now, in that class of superconductors, it's approximately half of room temperature, which is a huge improvement. Compound, which actually has a transition temperature of about 1/3 of room temperature. So it's not the record holder, but it's quite good. So you have these copper oxide planes with calcium, there happens to be calcium in here. Well, it turns out that there's a kind of structure which is formed in this kind of superconductor called a vortex, and it's the motion of these vortices. So we need to think about recuperate high current between these three different grids. And this is one purpose for which already superconducting switches, I think they're not actually in use, but they're being built, probably at least hundreds of miles. Most of it goes through ordinary copper, standard transmission lines. The last 1 kilometre is done by high temperature superconductor. That's really just a because you do have to cool them down to something like 50 to 77 K, where they work appropriately. Well, some of my colleagues at Argonne National Lab, importantly, you have to get an increase in the critical current. Microscopic theory, you need to work out which are the microscopic conditions that are best for pinning of the vortices. One important line. And a large critical current. Well, the problem there, we don't actually understand superconductivity in the cuprates, and in particular, the cuprates, the effect of the ionic lattice is either zero or at best secondary. So somehow you've got to be able to get superconductivity out of the cooler. Most of my theoretical colleagues who've been working in this area, do we understand the mechanism of high temperature superconductivity? You'll get the answer yes. You then ask of high temperature superconductivity. If we can combinations of 5 elements, are there something like 10 to the 10? That means, in terms of person years of research, something like 1 million person years save by making Cooper pairs. If you can somehow save that, get rid of some of that repulsion, then that gives you an effective attraction to all intents and purposes. You want a strongly layered. In principle, superconductors could greatly improve the electrical grid and do a lot of other things for us by saving a large fraction of the energy currently dissipated in transmission. However, the robust superconductivity at room temperature, and as I previously said, if you can, that would allow you to produce a lot of really practical, everyday applications. So, in fact, I think this is one area where I really can justify spending a lot of my research time on a very abstract topic. Well, of course, the question people always... Instead, there's one other thing I should just mention before I... Very, very interesting one. So that's yet one more application. So the question, of course, that everyone asks is, will we have room temperature superconductivity I sort of suspect that if you simply ask, will we have it during my lifetime, the answer is probably no. However, looking around the room, my answer would
Okay. Okay, thank you very much, Tony, for this very interesting and motivating talk. There is time for a few questions from the audience.
There has been this
talking about the iron selenide materials, perhaps?
maybe
yes.
it's that, and how this fits in your picture. Or
It's not okay, thank you. So the question was about the class of iron selenide materials, which was, as you say, originally discovered in China to be a relatively high temperature superconductor, about a third of room temperature, perhaps a little less. And the question, how does that fit into? The answer is we don't know. Right? One possibility, yes, essentially, a member of talking about is the lattice of the superconductor itself. But in this case, it turns out that you only get this effect when the iron selenide is laid across a substrate of, for example, strontium titanate, and it may actually be the ions of the strontium titanate lattice which are producing the polarization which is necessary. That's only one possibility. There are many others, and I think right now one has to say there's no general agreement about how that works.
Thank you.
The idea that I have been trying to explore, along with other people, is that because you're dealing with a strongly interacting system, much more strongly correlated than in the traditional superconductors, you have a large amount of... We asked questions by journalists, and one of the questions was, why do you rob banks? And his reply was quite simply, because that's where the money is. So the analogue is a really subtle principle in physics, and stored in conducting. Yes, you do reduce the energy in the mid-infrared peak. So it's, I think, at least a reasonable conjecture that at least in that area of the phase diagram, the mechanism of formation of Cooper pairs is a reduction of energy in the mid-infrared peak. But of course, it's going to take a lot more, much greater number of experiments to really establish that.
Very well. There is a question up there.
Yeah. Hi, thanks for the talk. The question is, and this is a limit, but theoretically certain limit, or in principle could be any value.
Okay, that's a very interesting question. And had you asked me that question in January of 2014, I would have said, well, pretty much yes. Yes, there is a limit, and it's the so-called Macmillan limit, which was set by my late colleague, Bill Macmillan at the University of Illinois, because experimentally in the hydrogen sulfide and other sulfide compounds, we found a much higher transition temperature, and we think these superconductors do work according to the BCS mechanism. And well, I should say incidentally, it's rather impressive that this high TC was not found by just random experiments. There are a couple of very light and very tight. You have very tight, you can go higher than that. And in fact, people are actively speculating that if we can make the right kind of compounds, then at least at 1 million times atmospheric pressure, they will be superconducting at room temperature. But so far, no one's done it.
Thanks.
There are more questions? I have one question.
That we have a reasonably accurate microscopic description of the sample. You take take two layers of single planes of graphene. The single plane by itself has a lot of interesting properties. The even more interesting is when you twist one of them relative to the other. Fascinating.
but how much people are at that? And do you think that...
As I pointed out, to go to search all the possible compounds consisting, say, of up to 5 elements by simply human classical computing or quantum computing or machine learning or whatever, you have to have the right input. And the right input in this case really is some idea of what is going to be the essential physical rules. Right now, as I've said, we really don't have that. So I think until we actually at least have some kind of idea of what are the essential ingredients, as it were, then even these machines